Hello everyone, my name is Sayan and today I will be presenting a summary of my PhD work on energy efficient data fusion techniques in wireless sensor networks. This is done under the guidance of my research supervisor, Professor Nilesh B. Mehta. This is an outline of what I am going to talk about here today. First, I will discuss the issue of energy efficiency in the context of wireless sensor networks. Then I will move to the first problem which I have worked on. It involves estimation using energy harvesting wireless sensor networks. Here I will discuss the two schemes which I have studied. Then I will move to the second part of my work, which deals with detection using wireless sensor networks. And under this section, I will discuss the two problems which I have worked on. And then I will conclude this presentation. As you all know, a wireless sensor network consists of a network of nodes that sense and collect data. In this work, we consider the following framework where there are n nodes in a network which observe some parameter and they transmit their recorded observations to a fusion node which performs data fusion. Here by data fusion we mean parameter estimation or event detection. Such a framework has several practical applications that include environmental monitoring, surveillance, industrial monitoring, and spectrum sensing in cognitive radio networks. Now, the nodes in these kinds of networks have a limited onboard battery energy capacity. So, the batteries will be exhausted eventually, the nodes will die out, and the performance of the network will be affected. Energy efficient techniques aims to make the batteries last longer. For example, censoring is an energy efficient scheme in which the nodes transmit only if they see favorable conditions. Now, these favorable conditions can be the channel power gain experienced by the node or the quality of the observation recorded by the node. The key idea behind censoring is that they make the nodes transmit less. As a result of this, the nodes can conserve energy and hence they can enhance their lifetime. Now, let us understand how censoring works and let us see if it has any trade-offs. We showcase censoring with an example. Here we talk about channel-based censoring. We have 4 nodes in a network which observe some parameter S. They record their measurements x1, x2, x3, x4 and they transmit these measurements to a fusion node which generates an estimate S hat of S. In censoring, a node will only transmit if the channel power gain exceeds a censoring threshold theta. In this example, Hi is the channel power gain for node I and a node will only transmit if its channel power gain will exceed theta. So you can see that based on these relations, only nodes 1 and 3 are eligible for transmission and they will transmit their measurements to a fusion node. Now, if you increase the censoring threshold theta, the nodes will transmit less often, so it will enhance their lifetime. However, as the fusion node will be receiving measurements from less number of nodes, the quality of estimation will be affected. Mean squared error, which measures the quality of an estimate, that will increase. Thus, although increasing theta enhances the lifetime, the performance will be affected. Now, these energy efficient schemes enhance the lifetime of the nodes, but the lifetime of the nodes is still finite. So the nodes will die out eventually. Energy harvesting sensor nodes, on the other hand, eliminates the problem of limited lifetime in wireless sensor networks. Here, the nodes can recharge their batteries from ambient sources. Thus, even if the node's batteries are exhausted, they can always recharge and get back into operation. Thus, energy harvesting sensor nodes offer potentially infinite lifetime. However, as the energy available is random, the nodes can occasionally be unavailable due to lack of energy. Thus, randomness in the energy harvesting process creates a challenge in the design of such networks. Let's try to understand channel-based censoring in the context of energy harvesting wireless sensor networks. We show it with an example where there are 4 sensor nodes and theta I is the censoring threshold for node I. We define a node to be active if it has enough energy to transmit its measurement to the fusion node. So you can see in this figure, node 3 does not have enough energy to transmit its measurement to the fusion node. Now, among the 4 nodes, only the channel power gains of node 1 and node 3 exceed their respective censoring thresholds. So they are only eligible for transmission. However, as node 3 is inactive, only node 1 will send its measurement to the fusion node. Thus, here the decision to transmit is determined not only by the channel power gain but also by the available battery energy. This is in contrast with what is seen for conventional wireless sensor networks, where the decision to transmit was determined only by the channel power gain. Now let's try to understand the impact of censoring threshold when we study censoring with WSNs. If you increase the censoring threshold, the nodes will conserve energy. However, the fusion node will be receiving measurements from less number of nodes due to the increased censoring threshold. So this will increase the mean squared error. On the other hand, if you decrease censoring threshold, the nodes will attempt to transmit more, so they will run out of energy more often, and this will again increase the mean squared error. Thus, unlike the case observed for conventional wireless sensor networks, where there was a monotonic trade-off between censoring threshold and the mean squared error, in energy harvesting wireless sensor networks, we need to balance node availability and also the estimation quality. Thus, the trade-offs are fundamentally different, and hence censoring needs to be revisited for energy harvesting wireless sensor networks. Now let's study its behavior. This is the system model which we have used for the problem of estimation. ST is the random parameter which is observed by n EH nodes. T denotes the index of the measurement round. At each measurement round, the EH nodes makes a measurement about ST. The measurement at the ith sensor EH node contains ST and the corresponding observation noise VIT. Once the EH nodes record their measurements, they transmit them to the fusion node over parallel orthogonal channels which experience independent but not identical Rayleigh fading. Once the fusion node receives these estimates, it computes an estimate. Once the fusion node receives these measurements, it computes an estimate S hat T of ST. This process again repeats in the next measurement round. The energy harvesting process is stationary, ergodic, and is assumed to be IID across the nodes. YIT is the signal received at the fusion node from node I at measurement round T. It consists of an amplification factor alpha, the channel fading, the observation recorded by the EH nodes and the corresponding receiver noise. Now, the estimator which we have studied throughout our work is the linear minimum mean square error estimator. We wanted to study the behavior of the average mean square error or MSE bar. It can be obtained by averaging the instantaneous mean squared error across the set of transmitting nodes. This set of transmitting nodes is random because they are determined not only by the EH process but also by the channel power gains. Now, obtaining a closed form expression for MSE bar is analytically intractable. We will be deriving lower bounds for that, but before doing so, let's try to understand the behavior of an EH node under censoring. We call a node to be energy unconstrained if it is active in a measurement round with probability 1, else it is energy constrained. Now we state two results here that characterize when a node is energy constrained and what is the probability that it will transmit. First one deals, or the first result characterizes the regimes in which the nodes are energy constrained and energy unconstrained. Node I is energy constrained if its censoring threshold theta I is less than minus lambda I log rho. Here lambda I is the mean channel power gain of node I and rho is the ratio of the average harvested energy H bar to the average energy needed to transmit. It consists of the transmit power P and the transmit duration TTX. This result states that if you censor the node less, that means when theta I is less than minus lambda I log rho, the nodes will attempt to transmit more due to the lower censoring threshold. They will run out of energy more often and they will be energy constrained. On the other hand, if you censor the nodes more, that means if theta I is less than minus lambda I log rho, the higher censoring threshold will prevent the nodes from transmitting. They will conserve energy and they will be energy unconstrained. The next result deals with the probability that a node transmits in a measurement round. As seen for the first result, it has different characterizations when the nodes are energy constrained and when the nodes are energy unconstrained. Now, using these two results, we can obtain a lower bound on the average mean squared error. Now, to gain insights, we will only show the results for the IID case. By IID case, we mean when the nodes experience independent and identical Rayleigh fading. As seen in the slide before, the lower bound on the average mean square error MSE bar has different characterizations when the nodes are energy constrained and when nodes are energy unconstrained. Using this lower bounds, we can also characterize the optimum censoring threshold that minimizes the bound. When the nodes experience independent and non-identical fading, this is the expression for the optimum censoring threshold. As you can see, they are different for different nodes. They depend on the mean channel power gain of the nodes and the ratio of the average energy harvested to the energy needed for transmission. Interestingly, at the optimum censoring thresholds, the nodes just become energy unconstrained. The intuition behind this is as follows. You censor the node just enough so that they are active with a probability 1. Now let's see how the censoring scheme behaves. We plot the average mean squared error as a function of the censoring threshold theta for a network of 30 sensor nodes and where the nodes experience independent and identical Rayleigh fading with a mean channel power gain of unity. We show both the simulation results, which is indicated by markers, and the solid line, which shows our obtained lower bound. We show the results for two values of rho, 0.6 and 0.8. A higher value of rho basically means that more energy is harvested compared to the energy needed for transmission. First thing we would like to point out is that the lower bound tracks the simulation curve extremely well. Now, let's look at the behavior of the curves. Let us take rho is equal to 0.6. As you increase the censoring threshold theta, you can see that MAC bar decreases. This is unlike the case for conventional wireless sensor networks, where if you increase the censoring threshold theta, MAC bar will increase. Now this decrease goes on till the nodes just become energy unconstrained. Beyond this, if you increase the censoring threshold, MAC bar increases. This behavior was verified by the lower bound itself, and if you recall the previous slide, the optimum censoring threshold is the point where the nodes just become energy unconstrained. A similar behavior is seen when rho equals to 0.8 also. Interestingly, and as expected, a higher value of rho means that you will obtain a lower MAC bar. The key takeaway from this slide is that the behavior of average mean square error MAC bar is not monotonic in the censoring threshold theta, unlike conventional wireless sensor networks. Now, censoring basically aims to make the nodes with larger channel power gains transmit. In principle, that can also be achieved with a similar scheme called opportunistic, with a different scheme called opportunistic subset selection. In censoring, whether a node will transmit or not depended on the censoring threshold. In opportunistic subset selection, the nodes are ordered in the decreasing order of their channel power gains, and we select a certain and a certain subset of them is selected for transmission. For example, we only want to make the nodes with the k largest channel power gains transmit. We refer to k as the subset size. For example, here you have 4 sensor nodes in the network, and we want to transmit the nodes with the 3 largest channel power gains. Based on this ordering, you can see that nodes 1, 3, and 4 are eligible for transmission. Now, if you decrease the subset size k, the node will be selected less often for transmission, so they can conserve energy, so their lifetime will improve. However, as the fusion node will be receiving measurements from less number of nodes, the mean squared error will increase. Thus, here also you gain lifetime, but you do so at the cost of performance. Before going into the details of the scheme for energy harvesting wireless sensor networks, let's try to first understand how such an ordered transmission scheme can be realized. This brings us to the timer-based scheme. In the timer-based scheme, each node maintains a timer Ti, which is a monotone, non-increasing function of a locally computed real number called metric. Higher the value of metric, lower the timer, and the node will transmit when their timer expires. This timer-based scheme ensures that the nodes can transmit in the decreasing order of their metrics without knowing the metric of any other node. For example, in opportunistic subset selection, the metric is the channel power gain. If you have a network with 4 sensor nodes with the channel power gains of the nodes following this ordering, you will see that the timer for node 3 expires first, followed by node 1, node 4, and node 2. Thus, the timer-based scheme ensures that the nodes can transmit in the decreasing order of their channel power gains without knowing the channel power gain of any other node. Now let's try to see how opportunistic subset selection can be realized for energy harvesting wireless sensor networks. Let's take an example where you have 4 nodes in a network and you want to transmit the nodes with the 2 largest channel power gains. Now, depending on how the nodes are ordered, we can have 2 possible realizations. The first realization is called ordered then active, or OTA. In this case, the nodes are ordered irrespective of whether they're active or not, and once the nodes are ordered, the k largest among them will transmit if they are active. For example, since we want to make the nodes with the 2 largest channel power gains transmit, here node 1 and node 3 are eligible for transmission. However, as node 3 is inactive, node 1 will only transmit to the fusion node. The second realization is called active then order. Here the ordering will happen only across the nodes which are active. So here only node 1, 4 and 2 will take part in the ordering process, and node 1 and node 4 are eligible for transmission and they will transmit their measurements to the fusion node. Thus, in hindsight, active then order looks to be better than order than active, because in active then order, or ATO, you take the battery energy status of the nodes before ordering them. As before, it is possible to obtain a lower bound on the mean square error for OTA and ATO. We are showing the results for the IID case since they are easy to visualize. As you can see, there are different characterizations when the nodes are energy unconstrained and when the nodes are energy constrained. K less than equal to n rho denotes when the subset size is less, the nodes will be selected less often, so they can conserve energy and they are energy unconstrained. On the other hand, if the subset size is more than n rho, the nodes will be selected more often and so they will be energy constrained. Using these 2 lower bounds, we can also numerically compute the optimal subset size k, which minimizes these lower bounds. The lower bound for ATO can be characterized similarly. Since it's quite involved, we are not showing it here. Even for the IID case, it's quite involved. Now let's try to understand how these 2 schemes behave. We plot average mean square error MSE bar as a function of the number of sensors selected for transmission, K. This is also the subset size. And we do this for a network of 30 sensor nodes, with rho being 0.6 and the nodes experiencing IID fading with a mean channel power gain of unity. We show the simulation results as well as our obtained lower bound. As you can see, as K increases, the average mean square error decreases because more nodes are selected for transmission. However, this decrease in MSE bar continues up to a point when the nodes are just energy unconstrained. Beyond this point, when the nodes become energy constrained, constrained, we can see that OTA outperforms ATO. This happens because when the nodes become energy constrained, the probability that a node is active is more for OTA than for ATO. This can be explained as follows. In ATO, only the active nodes are selected for transmission. This essentially acts as a negative feedback and further lowers the probability that a node is active. This is not the case for OTA, and as a result of this, the probability that a node is active is more for OTA than for ATO when the nodes are energy constrained. Thus, the key takeaway from this slide is that when the nodes are energy constrained, counterintuitively, OTA outperforms ATO. Now let's try to benchmark the performance of OTA and censoring. We plot minimum average mean squared error MSE bar as a function of the ratio of the average harvested energy to the energy needed for transmission. So the higher the value of this rho, more is the average harvested energy compared to the energy needed for transmission. So a lower value of rho indicates that the nodes are energy starved. These results are shown when the nodes experience independent and not identical Rayleigh fading, with the mean channel power gain of node I being 0.9 whole to the power I, where 1 less than equal to I less than equal to n. As you can see, when the number of nodes are less and the nodes are energy starved, OTA yields a lower error probability, lower MSE bar compared to censoring. This happens because in this particular regime, probability that a single node transmits determines the higher the probability that a single node transmits, less is the minimum MSE bar. Now, it can be shown that in this regime, the probability that a single node transmits is more for OTA than for censoring, and as a result of this, OTA has a lower minimum MSE bar than censoring. However, as the number of nodes increase, the performance of these two schemes are the same. This particular difference is at the 4th decimal place and is completely negligible. So the key takeaway from this slide is that when the number of nodes are less, OTA outperforms censoring. Now, let's summarize what we have found when we studied energy efficient estimation with energy harvesting wireless sensor networks. We found that the conventional monotonic trade-off between lifetime and performance is no longer observed when we studied these channel-based energy efficient schemes in energy harvesting wireless sensor networks. Rather, the focus shifts towards balancing the node availability and getting a better estimate. When we studied censoring in energy harvesting wireless sensor networks, we obtained a lower bound on the average mean squared error MSE bar, and using it, we showed that the optimum censoring threshold is high enough just to make the nodes energy unconstrained. When we studied opportunistic subset selection in energy harvesting wireless sensor networks, we proposed two novel variants, OTA and ATO. They differed in their consideration of the battery energies before the nodes were ordered. We found that OTA, in which the nodes are ordered irrespective of taking their channel power, irrespective of their battery energy status, outperforms ATO, in which the nodes are ordered after taking their battery energy into consideration when the nodes are energy starved. Furthermore, we also found out that OTA outperforms censoring when the energy harvested is less and the number of nodes are less. We now move on to the second part of our work, which focuses on detection with wireless sensor networks. Before going into the problem, we first want to set up the detection framework which we have used throughout this part. we focus on the binary hypothesis testing framework. In this framework, there are n sensor nodes which makes measurements y1, y2 up to yn. They transmit to the fusion node, which based on the received measurements, it decides between H1 or H0. Here H1 can denote the presence of an object, or H0 denotes its absence. Such a framework has several practical applications, which include spectrum sensing in cognitive radio networks, in which H1 can denote the presence of the primary signal and H0 its absence. Target detection, where H1 can denote the presence of the target and H0 its absence. Now, when the measurements are independent and identically distributed condition on the hypothesis, the detection framework is as follows. Once each node records the measurement, they compute a local log likelihood ratio, or LLR, denoted by Li. They transmit these LLRs to the fusion node, which sums them up, compares them to a threshold, which is determined by the probabilities of the hypothesis and the cost functions, and based on that, it decides between H1 or H0. Now, in the conventional scheme, every time a fusion node has to make a decision, all the nodes transmit to the fusion node. Thus, the node's batteries die out quickly. Now, the question now comes whether it is possible to make a decision with fewer transmissions. This brings us to the ordered transmission scheme. In ordered transmission scheme, the nodes transmit in the decreasing order of their absolute values of LLRs. Thus, if you recall the discussion from the previous section, this can be realized using the timer-based scheme, with the metric being mod of Li. Here we define mod L square bracket I as the ith largest absolute value of the LLR. Thus, mod L square bracket 1 denotes the largest absolute value of the LLR, mod L square bracket 2 denotes the second largest absolute value of the LLR, and so on. We denote square bracket I as the node with the ith largest absolute value of the LLR. When the node's timer expires, it transmits its LLR to the fusion node. Every time the fusion node receives an LLR, it tries to make a decision. Now let's try to understand how it makes a decision. We show that with an example. We have a network with 4 sensor nodes, and the best node will send its LLR to the fusion node. The fusion node will decide H1 if the LLR exceeds an upper threshold, or it will decide H0 if it is below a lower threshold. If it lies between these two, it will wait for the next transmission. Note that these two thresholds are calculated based on the fact that the absolute values of the remaining 3 LLRs is less than the absolute value of the received LLR. Now, if the fusion node is able to make a decision, it broadcasts a control signal to the remaining nodes to stop their transmission. However, if it is unable to make a decision, the second best node will send its LLR to the fusion node. The fusion node will sum up the 2 received LLRs, compare them to the upper and lower thresholds. It might decide, or it might wait for the next transmission. And this process goes on until a decision has been made. Now, this ordered transmission scheme and its associated decision rules exploit some key ideas. Let's try to go over them one by one. First thing which it exploits is the decision statistic is separable into individual node LLRs. Furthermore, larger the absolute value of the LLR, more will be its impact on the decision statistic. For example, a large negative value of the LLR will drive the decision statistic towards a negative value. Thus, a larger absolute value of the LLR will make for a more informative measurement, and this will make its metric larger. Thus, in order transmission scheme, the key aim is to make the nodes with the more informative measurement transmit earlier. Now the question is what to transmit when the node's timer expires. Since the final decision statistic is in terms of LLRs, the node will transmit its LLR. Now, what are the decision rules that needs to be used at the fusion node? The key idea behind the decision rules at the fusion node is to bound the decision statistic in terms of what you have received and what you are yet to receive. For example, if you have received k-based LLRs, you know that the absolute values of the remaining n-k LLRs will be always less than the absolute value of the k received LLR. And you can use this to bound the decision statistic. Using all these ideas, it is proven that you can save at least 50% of the transmissions while attaining the same detection error probability. Thus, not only do you save energy, but you do so without any impact on the performance. Thus, the order transmission scheme achieves energy efficiency without compromising the performance. However, it faces several challenges when you try to implement it in energy harvesting wireless sensor networks. The first is when the node will miss its transmission. Let's show how it faces the challenge. You have a network of 4 sensor nodes, and let us take the case when the second best node does not have enough energy to send its LLR. Now, as before, the best node will send its LLR to the fusion node. Fusion node might decide or might wait for the next transmission. Now, when the second best node is unable to transmit its LLR to the fusion node does not know that. So when the third best node sends its LLR to the fusion node, it will think that the second best node transmitted. Thus, the decision threshold that it will try to compute will be totally wrong. And if you miss a single transmission, the order transmission scheme will break down. However, it is possible to address this challenge. And this brings us to the first contribution which we made for order transmission with WSNs. We propose a new order transmission scheme called LLEH-OTS, whose full form is LLR-based energy harvesting order transmission scheme, which can address the problem of missing transmission. Here, if a node is unable to send its LLR, it sends a pilot signal. Here, a pilot signal consumes very less energy. And how it helps, we will show that with an example. Again, you take the previous example of 4 sensor nodes with the second best node unable to transmit its LLR. Now, the best node sends LLR to the fusion node. It might decide or it might wait. When it waits, the second best node sends a low energy pilot signal. This does not contain any information. It just tells the fusion node that the second best node has missed its turn to transmit. Now, when the fusion node receives the LLR from the third best node, it knows that the absolute value of the missing LLR will be less than the absolute value of the first received LLR. Using this, it can tell the interval in which the missing LLR can lie. And we can use this information to compute the decision thresholds. Thus, even if a node has missed its transmission, which can be a frequent occurrence for energy harvesting wireless sensor networks, it is still possible to implement the order transmission scheme. Now, the metric for the LLEH OTS is the absolute value of the log likelihood ratio. Now, we want to study how much role the metric plays in the design of the order transmission scheme. On that note, we investigate the binary hypothesis testing problem with Gaussian statistics, where the distributions under the two hypotheses have zero mean but different variances. In this case, the decision statistic is basically a sum of the squares of the measurements. And you can show that yi square is proportional to the LR at node I. Now, the larger the value of yi square, larger the value of the corresponding LR, and the more impact will be on the decision statistic. Thus, we can order based on yi square, or we can order based on Li, they are the same. And this is in contrast with the previous LLEH OTS case, where the ordering was based on the absolute values of the LLRs. Now, in this new metric, let's see how it handles the missing transmissions. We call this new order transmission scheme as NNEH OTS, or non-negative metric based EH OTS. In this case, the metric is yi square, and a node will transmit yi square if it has energy, else it sends a pilot signal. Now, what happens here? If you take the previous example where node 2 does not have, now first thing which we would like to point out is here the metric is directly sent to the fusion node. This is unlike the previous case where the ordering was based on mod Li, which was the metric, and what you sent was Li. Here you order based on yi square and you send yi square to the fusion node. Now what it does is, if a node misses its transmission, the fusion node will have a better estimate of the range in which the missing metric can lie. Here there is no sign ambiguity which was observed for LLEH OTS. In LLEH OTS, you only use the previously received transmission to determine the range in which the missing measurement can lie. In NNEH OTS, due to metric being sent itself, you can not only use the previous transmission, but also the next transmission and have a better estimate of the range in which the missing metric can lie. And that actually improves the scheme by a significant amount. We will show how it does with two results here. We have plotted first the average number of transmission as the function of the probability that a node misses a transmission. We show the results for the conventional scheme, LLEH OTS and NNEH OTS for network with 10 sensor nodes. You can see that both the ordered transmission scheme require significantly fewer transmissions compared to the conventional scheme. For example, when the node misses with transmission with a probability of 0.2, where the conventional scheme requires around 8 transmissions to make a decision, LLEH OTS scheme requires around 5 transmissions, and NNEH OTS scheme requires around 3 transmissions to make a decision. Now, NNEH OTS improves upon LLEH OTS because when a node misses a transmission, the fusion node has a better estimate of the range in which a missing metric can lie, and it can use it to make the decisions much faster. Furthermore, you can see that as you increase the probability that a node will miss a transmission, the average number of transmissions for LLEH OTS and NNEH OTS initially increases. This happens because as the nodes miss their transmissions more often, the fusion node will require measurements from nodes with less informative measurements. As a result of this, it will require more transmissions to make a decision. However, as a node misses its transmission more often, or as the probability of a node missing transmission increases, This effect is no longer seen and the average number of transmissions for all the schemes decreases. Now, NH-OTS scheme improves upon LH-OTS scheme in terms of average number of transmissions. Now let's see how it fares in terms of error probability. We have plotted error probability as the function of a probability that a node misses its transmission for the conventional scheme LH-OTS and NH-OTS. LH-OTS attains the same error probability as the conventional scheme. So it saves transmissions and attains us the same error probability. On the other hand, in NH-OTS, not only saves transmissions, but it also attains a smaller error probability. This happens because, again, when a node misses its transmission, the fusion node has a better estimate of the range in which the missing metric can lie. Thus, in NH-OTS, not only achieves fewer transmissions, but it also achieves a smaller error probability. So it provides a surprisingly double benefit of smaller transmission and a smaller error probability. Now let's try to see the behavior of the schemes when we model the battery energy evolution across the nodes and also model the impact of the pilot transmissions. Here, we plot error probability as a function of the number of sensor nodes for the conventional scheme in which all nodes attempt to transmit, the sequential detection scheme in which the nodes transmit in a random order, and every time the fusion node receives a measurement or an LLR, it makes a decision. The decision thresholds are determined by the target false alarm and misdetection probabilities. We also show the results for LH-OTS and NH-OTS. These results are shown when rho is equal to half. That means the average harvested energy is half of the energy needed to transmit, and the pilot energy consumes an energy of 2% of the energy needed for transmission. In this case, error probability becomes the key measure of performance, because when you simulate the battery energy evolution, the smaller the number of transmissions, the nodes can save more energy, and this will effectively reduce the error probability. You can see that since the LH-OTS and the NH-OTS schemes require smaller number of transmissions to make a decision than both conventional scheme and sequential detection scheme, their error probability achieved is significantly lower than both of them. Thus, the lower the detection error probability for the scheme, the more energy efficient it is, and you can see that both our proposed schemes are more energy efficient than the conventional benchmarking schemes. Thus, when we studied order transmission scheme for detection with WSNs, we learned that even if the nodes miss their transmission, it is possible to implement order transmission scheme by introducing the concept of pilot transmissions. The first scheme we proposed, LH-OTS, achieves significantly fewer transmissions compared to the conventional scheme. We also proposed NH-OTS scheme, which is a refinement of LH-OTS for Gaussian statistics, and it not only achieved significantly fewer transmissions compared to LH-OTS, but also a smaller detection error probability, especially when the nodes miss their transmissions. We now focus on the last part of our work, which deals with order transmission scheme in presence of spatial correlation. As before, we consider the binary hypothesis testing framework with Gaussian statistics. Interestingly, here, the decision statistic has a very unique form. It is no longer separable across nodes. It consists of terms which are coupled between nodes. Here, R naught and mu naught are the covariance matrix and the mean vector under hypothesis 0, and mu1 and R1 are the mean vector and the covariance matrix under hypothesis 1. Since the decision statistic is not separable across the nodes, it is not obvious how we can order the transmissions. Thus even deciding the metric in presence of spatial correlation becomes a serious challenge. Now, we have results for both the case when the nodes have different mean vectors, and we have both different mean vectors and covariance matrices. However, a key intuition is observed for the case when the nodes have the same mean vectors and different covariance matrices. We will discuss these insights here. First, we note that when the nodes have same mean vectors and different covariance matrices, the decision statistic has a nice quadratic form. And this nice quadratic form essentially enables us to formulate some decision rules. But before going into them, we propose that for this case, the metric at a node is mod Zi, where Zi you can call it the mean shifted measurement at node I. Here, the nodes require the information about the mean to implement the scheme, but note that we have results and the decision rules for the case when the nodes only know the measurements. We are not showing them here in the interest of time, and also this case gives us more insights. Now, since the proposed metric is mod Zi, the node will transmit Zi and this identity to the fusion node when its turn to transmit comes. Now, we have two decision rules for the shifting covariance matrix case. We call them CovShift-OTS and CovShift-Refined-OTS. Now let's see what they are one by one. In CovShift-OTS, the key idea which we utilize is the very famous eigenvalue bounds. Since the decision statistic Z transpose GZ can be upper and lower bounded using the maximum and minimum eigenvalues of G, we use this upper and lower bound, and we can bound the decision statistic in terms of what you have received and what you are yet to receive. Thus, CovShift-OTS exploits the eigenvalue bound to upper and lower bound decision statistic, and then further bound it based on what you are received and what you are yet to receive. A refined approach is adopted for CovShift-Refined-OTS, where we can write the decision statistic in terms of what you are received, what you are yet to receive, and then in terms of the cross term between the yes received and yet to receive measurements. Now, this particular term, which corresponds to yet to be received measurements, is a quadratic term, and you can bound it using the eigenvalue bounds, which we showed it in the previous slide. The cross terms, which corresponds to the received and yet to receive measurements, can also be bounded. Although this approach is quite complicated, it yields much better results. Similarly, the decision rules when the two hypotheses have different mean vectors and covariance matrices can also be obtained by following the technique which we use for CovShift-Refined-OTS. Now, before going into the simulation results, we first explain what is called a product correlation model. We have used this model extensively in our simulations, and this is quite a general model which is used to model the dependencies between Gaussian random variables. In this case, the correlation coefficient between two nodes is given by theta I and theta j, where theta I and theta j are both constant, which are less than 1. Such a model is applicable when the node measurements are linearly attenuated, noise corrupted copies of a source signal. Now let's try to see the benefits of the order transmission scheme. We consider the shift in covariance matrix case in which the hypotheses are IID with variance gamma naught under hypothesis, where the measurements are IID with variance gamma naught under hypothesis 0, and under hypothesis 1, the measurement follow the product correlation model with variance gamma 1. The mean vectors are the same for the two hypotheses. We consider a network with 20 sensor nodes and we define SNR to be the ratio of the two variances. We plot the average number of transmissions as the function of SNR in dB. And we show results for the conventional scheme, the CovShift-OTS scheme, and the CovShift-Refined-OTS scheme. We have also obtained an upper bound on the CovShift-OTS scheme. We have not shown here because it's too involved, but the key idea from what we want, but the key idea which we want to convey is that when the SNR becomes high enough, you can see that both the schemes require around single transmission to make a decision. Not only that, even when the SNR is around 10 dB, for example, the CovShift-OTS and the CovShift-Refined-OTS scheme requires around 4 transmissions to make a decision, whereas the conventional scheme, in which all nodes transmit, will require around 20 transmissions to make a decision. Thus, both the order transmission scheme save around 80% of the transmissions. Thus, even with correlation, designing the metric efficiently enables us to save significant number of transmissions compared to the conventional scheme. Now, we also show the results for the case where the two hypotheses differ in both their mean vectors and covariance matrix. Here under hypothesis 0, the observations are equally correlated with the correlation coefficient of 0.5, and under hypothesis 1, the observations follow the product correlation model. The mean vector under hypothesis 0 is all 0 vector, and the mean vector under hypothesis 1 is an all mu vector. We plot the average number of transmissions as the function of the number of censoring thresholds for different values of mu, and we compare the performance of the conventional scheme and a proposed order transmission scheme. You can see that the proposed order transmission scheme requires significantly fewer transmissions compared to the conventional scheme, and with fewer transmissions requiring as the value increase the value of mu. For example, when there are 20 nodes in the network, when mu equal to 1, we require the order transmission scheme requires around 14 transmissions to make a decision. When mu equal to 3, the order transmission scheme requires around 10 transmissions to make a decision. And when mu equal to 5, the order transmission scheme requires around 8 transmissions to make a decision. Thus, it is possible to save as much as 60% of the number of transmissions compared to the conventional scheme. Thus, even when the hypotheses have different mean vectors and covariance matrices, order transmission scheme achieves significantly fewer transmissions compared to the conventional scheme. Finally, we want to discuss the case when the two hypotheses have different mean vectors but the same covariance matrix. Here, the decision statistic is basically a weighted combination of the measurements. The weights are basically defined by the mean vectors and the covariance matrices. Here, the metric becomes that the mod of that weighted combination, and as before, you can obtain the decision rule, which we call as mean shift OTS, and it basically bounds the decisions. It basically bounds the decision statistic in terms of what you have received and what you are yet to receive. As before, we have plotted the average number of transmissions, the function number of sensor nodes and we have done that for the conventional scheme and the mean-shift-OTS scheme. We have also obtained an upper bound for the mean-shift-OTS scheme, and you can see that the upper bound tracks the simulation curve quite well, and and by ordering the transmissions, we save significant number of transmissions compared to the conventional scheme. For example, when there are 20 nodes in a network, but the conventional scheme requires around 20 transmissions for the product correlation model, the mean-shift-OTS scheme requires around 10 transmissions to make a decision. Thus, even with correlation, it is possible to order the nodes and save significant number of transmissions compared to the conventional scheme without any increase in the detection error probability. Furthermore, we are also able to analytically characterize the average number of transmissions when the hypotheses have same mean vector but different covariance matrices and vice versa. Thus, the key takeaway from our study with correlation is that even if the nodes observations are dependent on each other and the decision statistics are not separable, it is still possible to intelligently devise the metric and derive the corresponding decision rules to make sure the ordering is still possible and you save significantly number of transmissions without any increase in the detection error probability. So, as an overall summary of what we have done in this work, we first studied channel-based energy efficient schemes for parameter estimation with energy harvesting wireless sensor networks and found out that unlike the case with conventional wireless sensor networks, the focus shifts towards balancing node availability and getting a better estimate. Furthermore, we studied detection using order transmissions for energy harvesting wireless sensor networks and showed that even if the nodes miss their transmission due to lack of energy, using the concept of prior transmissions, it is possible to save significantly fewer. It is possible to obtain not only fewer transmissions compared to the conventional scheme, but also a smaller error probability when the nodes miss their transmissions. Lastly, we showed that even in presence of spatial correlation, significant savings in the average number of transmissions can be achieved while having the same detection error probability as the conventional scheme in which all nodes transmit. These are the publications which have come out of this work. The blue ones denote the publications corresponding to the work on estimation. So in this conference paper, censoring is studied in much more detail with additional performance measures, and the journal paper provides much more insights on the performance of OTA and ATO schemes. The second journal, it deals with the order transmissions for detection in energy harvesting wireless sensor networks. It has more results and several new insights. The red ones denote the publications corresponding to the study of order transmission schemes for spatial correlation, and they both contain much more results and much more insights. So if you have any questions, please feel free to include that in the comment section. Thank you for listening.